This week's lecture will go over speed, change of direction, and agility abilities. We'll also look at the mechanics, neurophysiology, ways to develop speed and agility, and program design of speed and agility. Lastly, there will be an overview of drills for speed and agility that you can utilize when developing a training program. There are three important aspects of physical performance that can have a big impact on an athlete's performance and success. Speed is defined as the skills and abilities needed to achieve high movement velocities, while change of direction is defined as the skills and abilities needed to explosively change movement, direction, velocities, or modes. And lastly, agility is defined as the skills and abilities needed to change direction, velocity, or mode in response to a stimulus. The ability to outrun the competition is a hallmark of most athletic endeavors. In addition, the ability to change direction rapidly during an activity can mute the effect of an opponent's speed or provide both physical and tactical advantages on the playing field. We'll often use the word speed in sprinting and when quickly changing direction. However, the perceived quote-unquote speed may be a result of one quality or a combination of speed, agility, and change of direction. When we refer to sports movement, high-speed locomotion can be categorized as linear or multi-directional. In general, an athlete generating high speed linearly, we can refer to as sprinting. Sprinting is very important to track and field events, but is also important in team sports. However, most team sports are multi-directional. So team sports athletes' success partially depends on responding to changes of direction and agility. For instance, a running back may have to change direction multiple times or demonstrate agility to pass some sort of defender to score a touchdown. Speed requires the ability to accelerate and reach maximal velocity, while change of direction is decelerating and then reaccelerating. Although agility is often used interchangeably with change of direction, one thing that agility requires or is different from change of direction is the use of perceptual cognitive ability in combination with change of direction ability. The physical capacity to change direction may be a component of agility, but the perceptual cognitive component influences the physical demands of agility. Athlete success in these qualities is the product of an athlete's strength capacity combined with the ability to use this strength within the constraints of the activity. Within sprinting, the application of force allows the athlete to accelerate, attain high velocity, and try to maintain the high velocity. Moreover, the force and change of direction and agility requires effective application of force to decelerate and then reaccelerate in another direction. Remember that agility is in response to a stimulus such as a defender or dodging a ball. When developing a speed and agility program, you must be aware of the training choices regarding the development of physical characteristics that assist in promoting speed, change of direction, and agility. In order to execute movement techniques, athletes must apply force. Since there is generally limited available time to produce force during most sports play, there are two variables that describe force relative to the time available to produce force. Rate of force development, or RFD, is the development of maximal force in minimal time and is typically used as an index of explosive strength. The second variable, impulse, is the change in momentum resulting from a force measured as the product of force and time. A basic objective of training is to move the force-time curve up and to the left, generating greater impulse and momentum during the limited time over which force is applied. Part of speed and agility is the mechanics. Force represents the interaction of two physical objects, which means that it has both magnitude and directional components. Acceleration is the change in an object's velocity due to movement of mass. Practically, deceleration replaces negative acceleration in describing a change from high to lower velocity, where velocity describes both how fast an object is traveling and in what direction. Within sports, the ability to produce force rapidly is a more desirable trait than maximal force production. While the ability to generate high levels of maximal force can improve performance, most competitive scenarios do not occur within the time frame that allows an athlete to generate their maximal force. Generating a maximal force takes too long and takes at least 300 milliseconds, while most sports scenarios consume 0 to 200 milliseconds. This is why rate of force development may be a more useful measure of an athlete's explosive ability, as the rate of force development is the change in force divided by the change in time. You can see on the figure to the right the amount of force produced between untrained, heavy resistance trained, and explosive ballistic trained. For an object to change its location, force must be applied to produce a change in velocity. Athletes attempting to increase speeds through the production of force never apply forces instantaneously. Force is applied to the running surface over a period of time in the stance phase of sprinting or in the plant phase of changing direction. The length of time athletes are in this stance or plant phase is termed their ground contact time. The product of the time the force is applied to the ground and the amount of force applied is termed impulse. You can see here in the figures how the vertical and horizontal forces differ in magnitude when the acceleration phase is compared to the maximal velocity phase. Each graph represents the two different body positions and also demonstrates the concept of impulse during the braking phase, which is the negative horizontal force, and the propulsive phase, which is demonstrated by the positive horizontal force. The two phases of impulse are indicated by the vertical dotted line. Athletes can start from a variety of positions before sprinting, including stationary or moving. Baseball and softball players generally initiate all speed movements in a 2-point stance from a stationary position, while basketball players can initiate movement in a 2-point stance, but also from an active movement like jogging or running backwards. In football, a tight end can start their stance in a 3-point stance, and a lineman can be in a 4-point stance. So you can see the starting movement is sport dependent. The start from a 3-point stance should occur with the athlete in a comfortable position. The body weight should be evenly distributed between hands, feet, and knees. The arms should be in a straight alignment shoulder width apart, and the head and back should be aligned. Prior to initiating the start, the athlete should align the center of gravity above the lead leg, bend the front leg to nearly a 90-degree angle, and the rear leg at nearly 125 degrees. Move the hips shoulder width apart or slightly wider, and straighten both arms and place them slightly in front of both hands. The start occurs with an explosive drive force from both feet, with the rear leg moving first with a forward swing, and the front leg performs an extension. The opposite arm swings forward and up as the rear foot lifts up to increase momentum and reduce inertia. The forward lean of the trunk helps overcome inertia while accelerating from the starting position. Acceleration is the ability to rapidly increase velocity from the starting position. During the acceleration phase, the body gradually straightens and the angle of the shin decreases with each stride. Additionally, the stride length and rate increase as speed increases. As the ball of the foot makes contact with the surface and produces force, the foot should be in a dorsiflex position. The impact forces increase and ground contact time decreases. While the athlete is in maximal speed, the stride length and rate are maximized, and during the run, the torso remains erect. We can see that stride rate plays a more important role in top-end speed. So the application of high forces to the ground is vital for achieving high speeds, and that leg drive is enhanced by powerful arm action. Neuromuscular function is vital to sprint performance because the activity and the interaction from the central nervous system with the muscles influence the rate and strength of muscle contraction. When the athlete performs strength training, they are enhancing neural drive. Increases in neural drive are indicative of an increase in the rate at which action potentials occur, which are related to increases in both muscular force production and the rate of force production. The combination of strength training and plyometric training increases neural drive and may contribute to increases in the athlete's rate of force development and impulse generation. The stress shortening cycle is an eccentric concentric coupling phenomenon in which muscle tendon complexes are rapidly and forcibly lengthened and immediately shortened in a reactive or elastic fashion. This is relevant to sports that require running, jumping, and explosive changes in velocity. The stretch shortening cycle actions exploit two phenomena: 1. Intrinsic muscle tendon behavior, and 2. Force and length reflex feedback to the nervous system. Acutely, the stretch shortening cycle actions tend to increase mechanical efficiency and impulse via elastic energy recovery. When looking at it chronically, they upregulate muscle stiffness and enhance neuromuscular activation. Speed is the interaction of stride rate and stride length. The stride contains two steps or foot strikes, which are the points of contact between the foot and the ground. Stride rate is the number of steps that are taken with each leg during the distance of a run, while stride length is the distance traveled by each step. Elite sprinters have a stride rate of 4.63 strides per second and a stride length of 2.70 meters, while novice sprinters have a stride rate of 4.43 strides per second and a stride length of 2.56 meters. We see as stride rate increases, the time spent on the ground decreases, while time spent in flight is increased. If the athlete increases stride rate and the stride length remains constant, the athlete's speed will increase, and vice versa. Stride rate appears to be more important in determining the runner's maximum velocity than stride length is. Overall, successful sprinters tend to have a longer stride length due to properly directing forces into the ground while also having a higher stride rate. This suggests that rate of force development and proper biomechanics are two of the primary limiting factors influencing sprint performance. The goal of sprinting is to achieve optimal stride length and stride rate through the correct application of force into the ground. Some training objectives for increasing running speed is to emphasize brief ground support times as a means of achieving rapid stride rate. This will require the athlete to have high levels of explosive strength. To achieve this, it is required that the athlete have consistent exposure to speed training in a well-designed strength training program. Another objective is to emphasize the further development of the stretch shortening cycle as a means to increase the amplitude of impulse for each step of the sprint. High achievers at top speed sprinting produce high forces in a shorter stance phase using the stretch shortening cycle. The complete weightlifting movements and their derivatives are key exercises for overloading the stretch shortening cycle with forces greater than those produced during an open sprint. So let's take a look at agility performance and change of direction, specifically factors affecting change of direction and perceptual cognitive ability. The ground contact time and ground reaction force during the plant phase of a movement provide insight into the physical factors that affect change of direction performance, while perceptual cognitive factors should be considered when relating to agility. Change of direction and agility movements performed at cutting angles less than 75 degrees, which are associated with shorter ground contact times, benefit from training similar to speed training with regard to the physical demands. However, it will still be required to have perceptual cognitive training, such as a coach blowing a whistle to change directions. If a change of direction has a cutting angle of 75 degrees or more and longer ground contact time, you should consider increasing emphasis on eccentric strength and maximal strength. An athlete's measured change of direction ability may vary depending on the demand imposed by the chosen change of direction test. Some different change of direction tests include the reactive agility test, the 505 test, the pro agility test, and the t-test. Another consideration regarding change of direction ability is the orientation of the body leading into the deceleration, where the athlete comes to a stop, then the positioning as they subsequently reaccelerate out of the change of direction. The positioning of the trunk will influence the performance of the change of direction. The combination of the ability to decelerate, reorient the body to face or partially face the direction of intended travel, and then explosively reaccelerate that truly determines the change of direction ability. Change of direction ability can increase with increased hip extension velocity, low center of mass height, increased braking impulse and propulsive impulse, increased knee flexion when entering the change of direction, minimize trunk angular displacement, and increase lateral trunk tilt. There are several components of perceptual cognitive ability, such as visual scanning, anticipation, pattern recognition, knowledge of the situation, decision-making time and accuracy, and reaction time. Many of these aspects of development are sport-specific and may take a lot of experience or practice. For instance, once you know the opponent's pattern recognition, or recognize some sort of pattern, you can then have a quicker ability to change direction. So let's say you're a defender on the basketball court and the opponent performs a move on you and you get burned on it for the first time. They continue to do it throughout the course of the game, but towards the end of the game, you recognize the pattern or movement that they perform. And since you know the pattern, you are able to change directions quicker to stop the opponent from scoring or making some sort of play. The three goals of agility performance are enhanced perceptual cognitive ability in various situations and tactical scenarios, effective and rapid braking of one's momentum, and lastly, rapid reacceleration toward the new direction. Some things to emphasize is directing visual focus towards the opponent's shoulders, trunk, and hips to increase perceptual ability to anticipate the movement of a defensive or offensive opponent. Another thing to emphasize is orienting the body into a position that allows for effective application of force into the ground to maximize braking capacity and increasing the speed from an immediate stop and from some sort of movement, for example, shuffling. Sprint speed is underpinned by an athlete's ability to produce large forces within a brief period of time. Thus, the transfer of strength improvements from resistance training to sprinting may require an emphasis on the specificity of training. Even though it may be beneficial to increase maximal strength, remember that maximal strength takes too long to generate maximal force in competitive scenarios. So there should be a combination of strength and speed strength type of exercises, such as the clean, the snatch, and mid-thigh pulls. These exercises may enhance sprint performance through physiological adaptations such as muscular stiffness, enhanced rate force of development, and co-activation of the musculature surrounding the hips and knees. Speed drills assist the progression of proper form and technique in speed training, which lead to improved acceleration, maximal velocity, and speed endurance development. By performing speed drills, they provide a forum for speed techniques to be broken down into smaller segments and perfected at reduced speeds so that they may be transferred to maximal acceleration, velocity, and speed endurance training. As with any drill, you should know the purpose of each drill and be able to demonstrate it with proper form and technique. Preferably, drills should be performed when athletes are fully recovered and not fatigued from other types of training or practice. The table to the right gives you an example of a sprint training workout. Here are some different speed training drills that you can incorporate into the athlete speed training program. There will be a separate document that will go into further detail on the exercises, which you can use as a reference. A popular method of speed training is using some sort of resistance. This involves the athlete pulling a fellow athlete or implement that provides resistance such as sleds or a parachute. This type of drill forces the athlete to recruit more muscle fibers, which results in an augmentation of neural activation. This elevated response helps athletes increase speed when the resistance is removed through increased stride length and power output. One thing though is that resistances used should not decrease the athlete's standard speed by more than 10%, because greater resistance may affect running technique and therefore negate any potential benefit from resisted running. Here are the recommendations for resisted running drills. For distance, this is between 10 to 40 yards, and when we look at sets of repetitions, this is going to be between 3 to 4 sets of 4 to 8 repetitions. And lastly, with recovery, this is going to fall in the 90 to 120 seconds range. Another method of speed training is assisted. This type of training uses a sport core to help athletes run faster than they normally would. Assisted speed training can increase stride rate and length more than is generally possible. The purpose of this drill is for athletes to run faster than they would under routine circumstances by using an artificial mechanism to increase both stride rate and stride length. Athletes should not exceed 110% of their maximum running speed. If they do go over, stride length may be overextended, which will result in deceleration and a decrease in stride rate. When it comes to program design for speed training, it should be incorporated during the power phase of training. Remember that speed training is not designed for conditioning and that there is a longer work to rest ratio. The purpose of speed drills is the quality of work and not the quantity. When we are prescribing speed exercises, they follow the same concepts as resistance training. All right, so when we are thinking about this, you can structure your training programs through some sort of periodization model. Before implementing any agility training program, baseline measures of change of direction ability should be assessed so that progress may be tracked over time. There are numerous agility tests, but each will differ in the length of time needed to complete the test, the number of directional changes, and the primary direction of force application, such as lateral or front to back. Some examples of tests that can be utilized for assessing agility is the T-test, the Pro Agility test, or also called the 5-10-5 shuttle, and lastly, the Illinois test. Part of agility that can enhance an athlete's performance is by adding a perceptual cognitive component to common close skill change of direction drills. You've probably performed this in practices where you may be performing a drill and the coach will yell a command, use their whistle, or use an arrow or light for you to change directions. So as the athlete becomes more trained and experienced, you can turn these drills into small side games. Agility drills can utilize pre-marked distances such as lines, cones or domes, and ladders. Moreover, these drills will differ in distance covered, duration, number of directional changes, and movement patterns. Again, it is important for the athlete to have proper technique throughout the drill. So the head should stay in a neutral position with the eyes looking straight ahead. Athletes will often hyperextend the neck or tuck the chin down due to fatigue or habit. With any agility drill, any changes in direction should be initiated from the top down. So the head should turn in the intended direction first, followed by the rest of the body. Here are some different agility training drills that you can incorporate into the athlete's agility training program. There will be a separate document that will go into further detail on the exercises, which you can use as a reference. The selection of individual drills should be based on what an athlete might encounter in a game situation, such as the movement patterns and the distances encountered. The order of agility drills within a training session largely depends on the training status of the athlete or population being trained. In general, a novice athlete will perform fewer complex exercises, those of shorter duration and with fewer directional changes, prior to doing more complex ones, those longer in duration and with more directional changes. This allows the novice athlete to become more familiar with the movement patterns and physical characteristics needed to perform change of direction tasks. Advanced athletes could use this same exercise order with the less complex drills serving as a warm-up to get them ready for more advanced exercises. The advanced athlete may also go directly into complex drills at the start of the session, but perform initial repetitions at a lower intensity before going into maximal effort repetitions. When it comes to frequency, it is recommended to perform agility training at least 2 to 3 times per week. This can increase or decrease based on the athlete's training status and which season they are in. For intensity, you usually will prescribe an intensity based on 1RM, heart rate max, or VO2 max. However, for agility training, you don't have a set intensity in that athletes can perform agility drills at maximum or near maximum effort. When we kind of look at a single repetition, or kind of looking at volume, a single repetition constitutes completion of a drill one time through. So if you have an athlete perform 5 repetitions of ladder drills and 5 repetitions of cone drills, the total volume performed is 10 repetitions. In general, you will have the athlete perform around 5 drills, and with novice athletes, they may perform 5 to 10 repetitions for a drill, while advanced athletes may perform 5 to 25 repetitions per drill. Last thing we'll talk about is recovery periods, and recovery periods should be provided between repetitions and drills so that technique can be maintained. A work-to-rest ratio between 1 to 4 and 1 to 6 should provide adequate recovery. So for example, a drill lasting 15 seconds would use a recovery period of 1 to 2 minutes. Individuals who are less fit, or if the individual athlete is performing a more complex drill, they may require longer rest periods and as large as 1 to 20 work-to-rest ratio. In summary, speed is a critical component in training programs for sport performance. Speed training should focus on running technique, acceleration to maximal velocity, and speed endurance. Special consideration should be given to the utilization of proper form and technique. So remember, it's all about the quality of work and not the quantity. Also, athletes should not progress to more advanced drills until they have mastered fundamental speed drills. Furthermore, in summary, the frequent changes of direction performed in most field and court-based sports highlight the importance of agility. Agility involves quick changes of direction and speed. Therefore, it relies on the capacity to very quickly stop the body and restart movement. Like most other performance parameters, agility can be improved through a well-planned training program that utilizes acute program variables and the concept of specificity. Also, the development of skilled change of direction ability requires agility-specific interventions. Therefore, athletes should train with agility drills. Agility drills should be selected to match the distance athletes will cover in a game situation and the type of changes in speed and direction they are required to make. Also, to improve change of direction ability, agility drills need to be performed 2 or 3 times per week over the course of at least several weeks. Lastly, agility drills must always be performed at high intensity to be effective. The difficulty of agility training sessions can be manipulated through the number of drills performed and the length of the rest intervals.